Okay, so we are ready to start with the third lecture, which is still cryptographic preliminaries, but it's a different topic within cryptography. And it's quite a fascinating topic for me. I mean, I'm not exactly doing this area, but the other day I was watching a movie how they explain it to kids in primary school, and I really like it. So it's called zero knowledge proofs. What is a zero knowledge proof? So here I would be using a lot of material from a tutorial on zero knowledge proofs called a server of zero knowledge proofs with the application to cryptography. So I think it's a very nice survey for those who would like to familiarize themselves with this topic. But let's start a bit with let's start with some preliminaries. We already mentioned one-way functions. Easy to compute on every input. What is easy to compute? It means there is a polynomial time algorithm to compute. Yet difficult to invert, meaning given the output, it's very difficult to find the input on which the function was applied to produce that output. So any polynomial time randomized algorithm succeeds with negligible probability to, given the output, to find the original input. Okay, what does it mean difficult? Here we need to be careful. Because in computer science, we associate difficulty with anti-hardness. This is not the case for, this is not what we use for one-way functions. Why? Because anti-hardness means that there are some difficult instances. So in a problem, we have a lot of different instances, right? On which the problem can be applied. You know, graph coloring, we can have a lot of different graphs. Traveling salesman, we can have a lot of different city combinations and Hamiltonian paths. So every classical NP-hard problem would have a lot of instances. But it doesn't mean that all instances are equally hard to solve. NP-hardness means that there is at least one hard instance which would be very difficult to solve. It doesn't mean that all instances would be difficult to solve. NP-hardness doesn't mean that an average, a typical instance would be difficult to solve. So NP-hardness only talks about the worst case. That's not enough for us. We want the average case to be hard, not just the worst case. Because in cryptography, it's not enough that sometimes digital signatures would be difficult to break. We want digital signatures to be hard to break all the time, not just sometimes. So it's different from NP-hardness. So we also will be using in the notation of collision-free hash function about which I was talking previously. So some examples of one-way functions which are used in cryptography and in particular in zero-proof systems. First example, multiplication of two large numbers. So given two large numbers, it's easy to calculate their product. And by easy, I mean it's polynomial with the number of bits representing each of these two numbers. However, if we take the product and we try to find the two numbers, that's a hard problem. Hard in the sense that there is no polynomial algorithm, polynomial with the number of bits in the product, which would give us the factorization, the two factors together, whose product is together creating the given number. Like I take even, okay, one of my favorite prime numbers, 239. So 239, if I give you if I give you 239 and say I ask you to compute 239 square, you would be able to do it easily. If I give you that value and ask you, give me the factors, try to figure out okay, I'm not saying it's a square of some, I'm saying it's a product of two numbers. Give me those numbers. You would not be able to find those numbers easily. So that's a one-way function. Easy to compute one direction, difficult to compute the other direction. Another example is squaring modulo number. So we take a number which is a product of two prime numbers. So n. So we take some p and q prime numbers, compute their product, would be n, and now we build, we consider I think it would be the ring of numbers calculated by x square modulo n. So we take an input x, and we calculate the square, and we calculate the remainder modulo n. And that's the output. Now, if I give you x, you would be able to calculate the function very easily, very efficiently. If I give you the remainder and ask you, give me the x that produced the remainder, that's a hard problem. Okay, so that's just one-way functions. It's not the fun part yet. Now, so what is a zero-knowledge proof? First of all, what's a proof system? Suppose the prover wants to convince the verifier that a given statement is true. So the age, for example, okay, well, the example. I want to buy alcohol in a store. I need to provide the proof of age, right? So I want to convince the verifier that my age is within the certain range. I want to provide the proof that a person is vaccinated against certain disease, right? That's a proof. I want to say, I want to convince you that I possess some secret key. That's a proof. So a proof is called complete if an honest verifier will always be convinced of a true statement by an honest prover. A proof is sound if a cheating prover, so suppose I'm underage, but I'm saying my age is 21, okay? So I'm a cheating prover. Then I can only convince an honest verifier that some false statement is true with a small probability. I'm not requesting that the probability be 0. I'm okay with a small probability of cheating. Now, a proof system is interactive if the prover is allowed multiple rounds of communication with the verifier. So the verifier can be, okay, it's like security check. Okay, like first question, you answer, okay. Now the second question, okay. Now the third question. That's interactive proof. Now what is zero knowledge? So that was the proof system. Now the zero knowledge part. Zero knowledge means that not only I want to prove the statement, I want the verifier to learn nothing but the veracity of that statement. For example, I want to prove that my age is above 21. I don't want you to know what my age is. I just want to convince you that it's above 21. I don't want to disclose my age. I want to convince you that I possess a secret key. I don't want to show you the key. I don't want you to learn nothing except for the fact that I possess the key. So, formally speaking, a proof is called zero knowledge if the output of any strategy used by a curious verifier could also be produced by non-interactive calculation. So in other words, whatever information can be learned by interacting, by like, I'm a verifier, I'll be asking prover a lot of questions. All I can learn can also be extracted from the initial information without any interaction. In other words, I learn nothing apart from the statement itself and its veracity. I mean, usually the first reaction, is it even possible? How can I convince you that I have a secret without showing you that I have it? It's quite surprising result. Yes, I can, due to one-way functions. And what we are going to spend most time on in this lecture is I'm going to give you examples of different zero knowledge proof systems. So I'll be sort of trying to show that they indeed are proof systems, complete, sound, and they're also zero knowledge. And later I'll also explain, so zero knowledge is heavily used in blockchain. It's also used in many applications such as digital identities and verifiable credentials. All right, let's start. The first example is like is a simple example. A magical cave. So the cave has a magic door deep inside that opens only when you say a secret word. And it happens that the prover, Peggy, discovered or uncovered the secret word. Now, the verifier called Victor hears about this fact and wishes also to know the secret. So Peggy agrees to sell Victor the secret word for $1,000. Oh, for $1 million. However, before Victor is willing to pay that much money, Victor wants to make sure that Peggy does know the word, that Peggy is not cheating. Okay, how can Victor learn or make sure, get convinced that Peggy knows the word without learning the word? So here's the system to do it. Okay, by the way, just to make sure that's the shape of the system, right? So the magic word in the middle, it then opens only when you know the word. So here's the idea for Peggy. Victor will wait outside the cave while Peggy enters. Now, Peggy can choose path A or B at random. Right, so Victor doesn't know which path she has chosen. Then, okay, so you can see it in the illustration here. Right? So Peggy chooses one path at random, goes to the door and waits. Then Victor enters the cave and goes to the fork, and at the fork shouts, tells the Peggy which way he wants Peggy to return. He shouts, way A or way B. And Peggy would hear Victor, right? And if Victor shouts the same path for which Peggy entered, Peggy would come back the same way. If Victor shouts the other path, Peggy would say the secret word, the door would open, and Peggy would come out. So, completeness. Peggy will always be able to return along the required path, right? If she knows the secret, if Peggy is honest. Soundness. Let's suppose Peggy doesn't know the secret. What's the probability with which Peggy would be able to comply with Victor's request? Sorry? Yeah, 1/2. Yeah, 50. Exactly. Okay, you could say, well, 50 is still a big number, right? So it's like, it's too generous for a cheater. Okay, what we can do, we can repeat the tests multiple times. And Victor would only accept the statement as true if Peggy passes the test each time. Just once Peggy fails, Victor would reject. And this way, so 2 times, the probability would not be 50, it would be 25%. Then when 1/8, so 1/4, then 1/8, 1/16, so it's exponential, right? And we can get it as small as we want. We are not demanding that it will be 0, but we can get it as small as we want. Zero knowledge. Victor doesn't learn the secret word. Okay, so that was a simple example. Now let's take a look at more complicated examples of zero knowledge proofs, which I also use in practice. Example 2. A proof for graph isomorphism. What is a graph isomorphism? 2 graphs with the same set of nodes are called isomorphic if and only if there is a mapping between the nodes of the 2 graphs. So essentially, it's a mapping to itself, or a permutation, such that the edge in the first graph would correspond to the edge in the second graph after the permutation. Here's an example of the 2 graphs, right? So here we have a rectangle. Here we have this shape of a butterfly or something. Is it isomorphic? Can we have a mapping? It's the same nodes, right? Can we map the nodes of this graph to nodes of this graph so that the edges would correspond? The answer is yes. Maybe, I mean, it's nice sometimes when the students can explain why it's the case, please. Why there is an isomorphism? In this case, what's the mapping? All right, well, the mapping is written here. So this node maps to this node maps to this node. This node, however, maps to this node, and this node maps to this node, right? And then we have the same edges here as we have here. So the same connections between the nodes. So the 2 graphs are isomorphic. And, okay, so what you see here, this mapping is a permutation, right? It's a mapping between the nodes, the set of nodes, to the same set of nodes. Permutation. Now we can say that a graph is a random isomorphic copy of a different graph if it's obtained by picking a permutation, right? In just the notation. How can we use all this to create a zero knowledge proof system? So what's the idea? The thing about graph isomorphism is that if I know the permutation, I can easily verify it. So suppose we are given two graphs, and the two graphs are isomorphic. So let's denote the isomorphism between the two graphs. They are isomorphic, we know that. V as the prover, right? So, however, the thing is, if we don't know phi, it's very difficult to say in the general case if the two graphs are isomorphic. I mean, what we saw in the previous slide was just a very small scale, right? If we give like large scale two graphs and ask, are they isomorphic? And we don't give you the permutation, it's very easy to find out if there is such a permutation and what it is. That's the one-way function. So the idea of the proof is as following. We're executing 4 steps, certain number of times, and each time we are using independent random coin tosses. If the verifier completes all iterations successfully, then he accepts, otherwise one failure and the verifier rejects. So what happens at each step? The prover selects a random permutation and generates a new graph H, which is a random isomorphic copy of G1. So we have G0, G1. G1 isomorphic. Which are isomorphic. We take G1, we take a random permutation, and we produce a new graph H, which is isomorphic to G1. And the isomorphism is transitive, meaning it's also isomorphic to G0. Okay. Then the prover sends the graph to the verifier. The verifier chooses at random a coefficient, either 0 or 1, and sends it to the prover. Now, what happens is if the coefficient is equal to 1, then the prover sends the permutation to the verifier. Not the original permutation, not phi. Phi is the secret. It sends pi. This permutation to the verifier, not this permutation. If the coefficient, however, is 0, then the prover calculates pi times phi and sends that to the prover, to the verifier, sorry. Okay, so what happens is that the verifier gets all the data and calculates, checks if there is isomorphism between G alpha and H. I mean, how? If alpha is equal to 1, then the verifier does the same calculation that the prover earlier did. It just computes. So it gets pi from the prover. It takes G1, applies pi, gets H, and if it's the verifier already knows H, if it's the same H, then it works. The verifier accepts. If alpha is equal to 0, then the verifier takes G0, not G1, applies pi times phi, right? And pi times phi applied to G0 means that, phi applied to G0 is G1, and pi applied to G1 is again H. So the verifier would accept. This is the verification. Now properties, completeness. If a prover knows the original isomorphism, that is phi, then the prover will always be able to answer. Soundness, if a prover does not no phi, then again, the probability for one iteration. So if the prover doesn't know phi, it means that the prover will still be able to calculate a random isomorphic copy of G1. So if alpha is equal to 1, then the prover, cheating prover will still be able to send correct answer to the verifier. However, if alpha is equal to 0, then the prover would not be able to satisfy the request of the verifier. So with probability 1/2, the verification fails. And again, we can repeat it m times. So at the end, the probability, the prover who is cheating, who doesn't know the answer, would be able to answer the request with probability 1 to 1 divided by 2 to the n. So zero knowledge. It's also interesting to see that the whole scheme does not disclose phi. It only discloses pi times phi, and it's not possible because the verifier doesn't get pi. It only gets pi times phi. So from pi times phi, it's not, because we don't know pi, it's not possible to restore pi. And therefore, it's zero knowledge. So it's also possible to prove that actually the verifier doesn't learn anything which is not in the proof. In practice, I mean, okay, those are just some examples, but in practice, most zero-knowledge proof schemes are based on the Fiat-Shamir protocol. Okay, how does the Fiat-Shamir protocol work? There is initialization, it's yet another proof, right? System. Initialization. We have some trusted center, like some trusted authority, which selects and publishes n equal to the product of two prime numbers. So the trusted center keeps the two prime numbers secret, but discloses their product. And we know that factoring numbers is a hard problem, so it's given n, it's difficult to find p and q. Now, the prover selects a secret s, secret value, which is co-prime to n. So s is a number between 1 and n minus 1 including. And then the prover computes square root of s modulo n, which is like we denote as v, and discloses v as the public key together with so like publishes t, uses t. You can think of t as maybe like a ledger, open ledger or blockchain, right? So the prover can put the public value of v in the blockchain open to everyone. Now again, we know that it's a one-way function, so given v, we cannot easily calculate s. S is a secret, v is public. Again, p and q secret, s secret, n public and v public. Okay? So the goal is for the prover to convince the verifier that the prover possesses the private key s without disclosing s. So how can the prover do that? As usual, it's based on interactions, right? So the steps are executed a certain number of times, each time using independent random coin tosses. And if the verifier has completed all steps, he accepts. So that's common for many proof system, but what each step does is different. So each step consists of two phases. In the first phase, the prover chooses a random number and sends the square root modulo n of that random number to the verifier without disclosing r. Only x, only the square root. The verifier randomly selects a bit 0 or 1 and sends back to the prover. And then the phase 2 starts. In the second phase, the prover computes and sends to the verifier a value, which is either r if e is equal to 0, or it's equal to r times s modulo n if e is equal to 1. So then the verifier checks the following. If y is equal to 0, if y is equal to 0, or if y squared is not equal to x times v to the e modulo n, then the verifier rejects. Otherwise, the verifier accepts. And we go to the next iteration. So I mean, it's a bit involved, right? So let's take a look at a running example. Let's say that the center, the trusted center, picked P and Q, the two prime numbers, and calculated their product, which is 35. And the 35 is published to everyone, while 5 and 7 are kept secret. Now Peggy, the prover, secretly chooses 16. 16 is a coprime to 35 because they don't have any common denominator. She calculates 16 squared modulo 35, which is 11. And that's the public key of Peggy. Okay, let's take a look at how the protocol could run, say for 2 iterations. First iteration, Peggy randomly selects a value, say 10 in this example. She would calculate the value of 10 squared modulo 35, which is equal to 30, to Victor. And you can check that r squared 10 is indeed like modulo 35 is equal to 30. Okay. Victor randomly selects a bit, in this case 0, and sends back to Peggy. And since the bit is 0, Peggy just sends back r itself, which is 10. And Victor verifies that r squared is r squared modulo 35 is equal to 30. Then the second iteration starts. This time, Peggy selects a different value, r equal to 20. She would calculate the square of 20, modulo 35, which is equal to 15, and sends it to Victor. And this time, Victor selects not 0, but 1. And since Victor selected 1, Peggy computes S16 times R20 modulo 35 equal to 5 and sends back to Victor. And Victor verifies, indeed, that y squared, so meaning 5 squared is 25, and times and modulo 35 is the same as 15 times 11. So this is how it works. I mean, it's a bit involved, but this is how actually most practical zero knowledge proof works. So they use this kind of math. So the properties. Completeness, a prover who knows the secret key will always be able to answer the request correctly. As usual, in one iteration, a prover who doesn't know the answer, who doesn't know the secret number, would only be able to satisfy the request from the prover if E is equal to 0. If E is equal to 1, Peggy would not be able to correctly compute the answer. So the probability of failing in one iteration is again half. And the zero knowledge, at no step, Peggy discloses S itself. So the secret is safe. These are some examples of the zero knowledge proofs. And in several lectures further down the course, you'll see the application. Again, this is preliminary, so you have not seen how we are going to use it, but that you are going to see in the rest of the course. So thanks a lot for listening.